We are now going to create the layout for a 2-input NAND gate and 2-input NOR gate. For the NAND gate, you will notice that the two PMOS are in parallel and the NMOS are in series. Wherein for NOR gate, the two NMOS are in parallel and the two PMOS are in series. We'll start with the implementation of your NAND gate. For the implementation, we're going to use electric 6.03. As usual, be sure that the settings are correct. So for the technology, change that to MOCMOS sub, then change the units to 350. For the spice options, ensure that the model has been loaded. Otherwise, you can find the model inside your electric. So be sure to include this specific file. So once you are able to change the settings, you can now start with facet, edit facet. So new facet. So let's just name this as NAND layout. Okay, you can now start with the layout by placing two NMOS and two PMOS transistors. Since we're going to use the standard CMOS implementation of your two-input NAND gate, so you need to have two NMOS and two PMOS. For the PMOS, since you are to connect it in parallel, you should have a node in between your two transistors. So just use a metal 1 P active. So but before you place any other components, be sure to change the transistor size since we're going to implement let's try to implement 2:1 ratio between your PMOS and your NMOS. So as such, you need 1.6 micro for all your transistors. 1.6. I can check. So there are no errors. So you need to further connect two more on opposite sides of your PMOS and NMOS, as well as metal towel contact. So align the polysilicon for the NMOS and PMOS. That will be the input for your NAND gate. So check if there are errors. So there's still no errors. Connect the polysilicon as well as the active. Okay. So since we need to connect the two PMOS in parallel. So these two nodes, this node as well as the node on the other side must be connected. But if you're going to connect that using the active, then it would cross this polysilicon, resulting to a formed transistor. So you need a metal, so this should be a metal, so that it will be formed on the different layer. So it won't have any effect on your polysilicon. If you're going to use active and it crosses your polysilicon, eventually it will form a transistor. So check. So you notice that that is too close to your transistor. So you just need to adjust that. So these two transistors are now connected in parallel. From this diagram, between the connection of the two parallel PMOS, it should be connected the output of your circuit. So the output should be connected to your uh, in between your pull-up network and the pull-down network. So you need to have a connection in between your PMOS and your NMOS. So in this case, you need to connect this, and this will serve as your output. So you can extend it to this point, and it will now serve as your output. While this part will serve as your supply. Then you can, if you want, you can extend this for your inputs. This will now be your ground. So to include in your export, create export, start with the input A. This one will be export, create export, input B. So you have input A, input B. This will serve as your power VDD. This will be the ground. So create export, ground, label it as GND. Then you need to have your create export output. You can use F as your output. So this will be your layout for the NAND. So we're going to simulate if you were able to properly design the NAND gate. So first, check if there are errors. So there are no errors. We can now proceed with simulating this given layout. So to do that, we need to create a schematic. So edit, facet, new facet, schematic. So we can name this as NAND lay test. Okay. Since we're going to use schematic in the simulation, so you need to change your current technology to schematic analog, change units, change this to 2000 so you have 1 micro, and verify if there are changes in your spice options. So basically, you didn't change anything from the previous one, so it should have same default values. So you can now start with your spice. Of the voltage source, you can type 3.3. So we use control 0 to zoom out. Another voltage source for the pulse. Since we're going to have two inputs, you need to have two pulses. So one should have a value of 0, 3.3, 0, 1 nano, 1 nano. Let us use 20 nano and 40 nano for our input B. So for input A, we're just going to double the value from 2040 to 4080. So after having your two inputs, we need to monitor the input as well as the output. So for the monitoring, you need to have a voltage meter. So control C, control V, you just need to place the voltmeter, include one capacitor, change this to femtofarad, then the ground. So since basically the schematic are complete, so you just need to export. So new facet instance, the layout. So after placing the layout, do not forget to re-export everything. So you notice that all labels are now visible. We just need to connect the ground as well as the other circuit components. Input A, input B, connected to the ground, as well as your multimeters or your voltage. So you have basically connected all the components except for the transient analysis. So we can just use zero point 0.1 nano. We need to have one cycle for our input A, so 80 nano. We're just going to determine if we're able to generate the correct output for your NAND gate. So after placing the transient analysis, you can use write spice deck and all files NAND latest.cir, NAND latest. So to simulate the CRR file, you need to open the WinSpice software, file open, so NAND latest.cir. So you now have this values for or the graph for your input and output. For you to properly see the graphs, so you can arrange it in such a way that the most significant bit, for example, A will be assigned as the most significant bit and F as your output. So you can just use plot VF VB plus 4, and on the top of your plot will be A, so that will be plus 8. So as you can see, for the NAND gate, you only have a low input if both inputs are high. So in this case, we're able to um, prove that the layout are or the layout is correct.